Okay, good morning, students. Yeah. So today we'll be seeing about the inter-process communication. So IPC in operating system. Today we'll discuss about the introduction to inter-process communication and race condition and critical region. This is a important point in operating systems. So let us start with what is IPC or inter-process communication. We discussed in the first unit what is a process, what is a threads. Sometimes a process may communicate to other process. Threads of the process or process itself can communicate to other process to complete its work. So in operating system generally, the processes frequently need to communicate with each other process. For example, in a pipeline, the output of the first process must be passed to the second process. So on the down in the line. So there is a need for communication between process, preferably in well-structured way without using any interrupts. So we can understand that there are process. The process has to communicate to other process sometimes to complete the process. The output of one process may be communicate to others. Okay, so these are the thing is called inter-process communication. Process communicate to other process. We call it as inter-process communication. So to complete the one work, it will communicate the output of the completions absolutely depends on the output of the other process. Okay, there are three key issues are there in the IPCs. First one, how one process can pass information to another. That is a well structured way is given. The second one has to do with making sure that two or more processes do not get each other's way when engaging in critical activities. That's very, very important. The third concern is proper sequencing when dependencies are presented. So it has to be addressed properly. So inter-process communication nothing but the process, one process communicate to other process called inter-process communication. So that's the important key points here. Now we'll come to the core part, race conditions. So race conditions. First we'll look at the definition. The race condition occurs if two or more processes or threads access and manipulate the same data concurrently, and the output of the execution depends on the particular order in which the access takes place. For example, from the real-time example, you can understand what is race conditions. So we all have seen what to say. We all have seen the musical chairs when there is during the local festival like Diwali Pongal in our schools, in our local places, they conduct the musical chairs. Finally, one chair will be kept place and two people will be roaming around the chairs. When they start music, they will be roaming. They will play the music for some time. When they stop the music, the two persons will try to get the chairs, try to sit in the chairs. But only either of the one will win the musical chair. But the idea is the two people looking for a single chair is called race condition. The output is execution depends on the particular order in which the access takes place. Who gets the chair is called they are the winners. But we forgot about the winners. The two people are looking for a single process, or two people seeking for a single resource called race conditions. And we have a synchronization concept. The synchronization is needed to prevent the race condition from happening. That we'll see later. Okay. So here they given a technical example. Apart from the musical chair, they given a technical example with diagrams. So when a process wants to print a file, it enters the file name into a special directory called spooler directory. The center place is called spooler directory. If you want to print something, the process writes something into the spooler directory. The system takes the file from the spooler directory, it gets prints. Okay. So another process called printer daemon. So it checks whether if there is a file to be printed. If there, then it prints them. It removes from the entries. So The spooler directory, the process enter the file into the spooler directory. The printer daemon takes the file from spooler directory. So there are three files is waiting. So as printer, when the printer is available, the file ABC will be taken out, it will be printed. And once it is finished, it will be removed. Next program C will be taken for printed. Once it is over, it will be removed from the directory and the program N will be taken for the printer. Okay. So here the race condition is we have two people, two processes are there, process A, process B, which is the spooler directory is highly controlled by two variable called in and out. Out is the variable where the next file to be points to the next file to be printed. In is the variable which points to the next free slots. Okay, out the spooler daemon checks the out variable. The fourth is the next file to be printed. So once it's taken for printed, it will update as 5. So next free slot is there are 3 slots are filled. Next free slot is 7. Suppose assume that process A wants to write something, wants to print something into the spooler directory, want to put some file into spooler directory. So process A checks for the next free slot by looking at the variable. 7th is the next free slot. It assumes that next free slot is 7 and it go for some other work. And the process fee B also coming into the spooler directory. It checks the next free slot is 7. So it think we assume that 7th is the next free slots. Then it writes something into the file. Okay, and it's updated state. But process A, according to process A, next free slot is 7. After some time, process A comes back to the work. It rewrites the process B file. So process B will be waiting for the file, waiting for the files to be printed out, waiting for the output. That will never happen. This is called race conditions because that file, the data which is written by B is overwritten by process A. So this is what this condition is called race conditions. So process A checks the in variable before update the in variable. Process B also checks and writes something, and A also overwrites something. Okay. So what happens is the B will be waiting for the output that will never come. This is what called race conditions. Okay. The output depends on precisely who gets the slot. So process A reads the store the reads the variable in and stores the values in local variable called the next free slots. Process B also read in and gets A. It stores in the local variable called in the process B local variable called next free slots. The process B continues to run. It writes something into the file and I update into 8 and goes off. Eventually, the process A also coming again. So it writes overwrites the where the B was written and written as next free slot sets in variable as 8. Okay, the process proper is everything's happened correct. Only thing is the file written by B is overwritten. This condition is called race condition. So B will never receive any output. It will wait for the output which will never come. So B will hang up for around the print room for years. So it will never will come because the file of B has been rewritten by A. The slot is used by A process A. So situation like this where two or more process are waiting or reading or writing the same shared data and the final results depends on who runs precisely when are called race conditions. This situation is called race conditions. So now we look at the critical region. So race conditions, critical region is an important point in the inter-process communication. So in order to avoid the race condition, the people have introduced the concept called critical region and a mutual exclusion. Okay, the key to prevent the trouble here is in many other situations involving shared memory or shared files or shared everything else is to find a way to prohibit more than one process from reading and writing the shared data at the same time. So mutual excludes the some way of making sure that if one process using the shared variable or file, the other process will be excluded from doing the same thing. So we can avoid the race condition with the help of critical region in which they have introduced the concept called mutual exclusion. Let us look at what is critical region. But in computer, most of the files are shared by nature. So the variables, the memory, the hard disk, the printers, the printer memory, printer buffer, everything is shared in nature. So many times the race condition may appear. So the variable or shared file or shared memory is the part of the program where the shared memory is accessed is called critical region or critical sections. Okay. So what is critical section? Through this example, you can understand that. So this is the variable or this is the file which is shared, which can be shared by more than one process, process A, process B. Okay, this is a safe critical region. Only one variable, one process can allow to use the critical region. This is allowed when more than one process, 4 program or 4 users not allowed to access the critical region. This is what critical. The shared variable, when it used by only single process, we can say it is a critical region. So that process maybe 2 may not be allowed to access the thing. Process 3 may not be allowed. Process 4 may not be allowed to access the, not be same in the critical region. Okay, once process 1 is completed work, the process 2 or 3 or 4 can be allowed to use the critical region. So this is the timing diagram. For example, the process A is in critical region. Okay, so it enters the critical region at the time of T1 and leaves the critical region at the time of T3. So T1 to T3, the process A in critical region is using the same shared variable or shared memory. For example, process B at the time of T2, it tried to enter into critical region, but it is blocked because already A is in critical region. It is not allowed to enter into critical region, so B is blocked. After when A is leaves, the B is enter into critical region at the time of T3, and it uses it is in critical region for sometimes. Once work is over, at the time of T4, it leaves the critical region. So here the race condition is avoided with the help of critical region and mutual exclusion concept. So there are 4 conditions to have a good solutions. First one is no two process may be simultaneously inside the critical region. So when process A is in critical region, process B may not be allowed. When process B is in critical region, A may not be allowed. No assumption may be made about the speed and number of CPUs. So the speed, the time to complete, the number of CPU processor in your computer, it should be no assumption should be made. So no process running outside the critical region may be block the other process. So for example, A is in critical region, B is in non-critical region. The process which is running outside should not preempt, should not avoid any process in the block the critical region. No process should have a wait forever to enter into critical region. So for example, A may hold for a lifetime, though B will not be allowed to enter into critical region. This situation should be avoided. So critical region may be used for only short period of time. If it is a long time, then the other process may not get into the critical region, so that it cannot have completed work. So this is what today's topic. Okay, today we discussed about what is inter-process communications, introduction about the inter-process communications, and we discussed about the race conditions and the critical region is the concept to avoid the race condition. So that's all about today's class. Thank you, students. Have a good day.